I'll be right back. I'm going to grab an eraser. Okay. Can everyone hear me?
Yep.
Yeah.
Okay. I'm going to go in my email and open up a problem. And I'm going to share my screen so you all can see it. Am I already sharing my screen?
No.
Okay, good. The share screen button is lit up, but I didn't think I was. So wanted to double check. But yeah, I'll go open that up and we can go over a couple problems.
I can't see your screen. I just see you.
Okay, yeah, I'm gonna open up the problem and then share my screen. Let's start with the same problem we've been seeing a lot. Let me share my screen now. Okay, so y'all should be able to see that now.
Yeah, it's thinking that.
Yeah.
Yeah.
Yeah, so this is the problem that has killed everyone over and over and over.
Yep.
So let's start with a basic powers of 10 strategy. Usually you don't want to spend a long time on this if you're taking a test or something, but just to make sure that we are solving this correctly, it's worth it. So let's start by just doing a force diagram for the upper ball. So for the upper ball, I will go back to my whiteboard here in a second. We have 9 kilograms as the mass. We have total charge is 61 times 10 to the negative 6. And the tension is equal to 154 newtons. And the radius is equal to 0.32 meters. So it's already in meters. And to just start with this one, let's just round everything to the nearest logarithmic power of 10. I mentioned that in one of my earlier videos, but 3 rounds up, everything below 3 rounds down, and then you just calculate everything with powers of 10 that way. So if we do a free body diagram, we've got mg acting downward, and since they're opposite polarity, we've got the force of tension acting downward, and then the force of electricity acting downward, and the force of tension acting upward. And I don't know if you guys have the little participant screen open, but you can kind of see it. It's pretty small. I will, like I said, I will go back to my screen so you can see it once I have it written out. So then we get the equation that FE.
If it helps anyone, you can touch like your thing and touch the 3 dots and pin your video and see you big.
Okay, yeah. Let's see. Optimize share for full screen video clip chat. So you're saying that's on the more button?
Like that's something that we can do to see you without like you doing it.
Yeah, so that would be good for some people, because I'm kind of drawing this up.
Which
So FE plus MG is equal to FT. We know M and G. And so then M is about equal to, let's start writing the powers of 10. M is about equal to 10 kilograms. This is about equal to 10 to the negative fifth. Or sorry, 10 to the negative fourth. Yeah, let's do 10 to the negative fourth, because this would be 6.1 times 10 to the negative fifth, or 0.61 times 10 to the negative fourth, and it rounds up. T is about equal to, well, let's leave T alone because it's in newtons, and then R is about equal to 10 to the negative 1. So we've got, no, I'll do tension and 10 to the negative 2, or 10 to the 2 as well. So we've got FE plus MG equals FT. FT is about 10 to the 2. The 10 to the 2 is about equal to 10 times, and then G is 9.8, so that's about equal to 10. So you've got 100 plus FE. Well, FE is K over R squared times QQ. And then K is about equal to, what is it, 9 times 10 to the 9th? So 10 to the 10th. We've got 10 to the 10th over 10 to the negative 1 squared. This is equal to 10 to the negative 2. So that gives us 10 to the 12th times QQ. So we know that this has to be very close to 0, just because when we look at the powers of 10 over here, we've got 10 squared plus something is equal to 10 squared. So it's got to be at least a whole order of magnitude less. So it's less than or equal to 10 squared in magnitude. So working this, that means that this Q1, Q2 has to be less than or equal to 10 to the negative 10th in magnitude. So now I will just share that so we can see the process I got to that. Since they're roughly equal in mass and magnitude, that gives us a rough ballpark of 10 to the negative fifth is what we're going for. So can you all see that?
yes.
Okay. So if I go up here, but this is the calculation. We narrowed it down to be about 10 to the negative fifth. It could be anything less than that, and it will be in the right ballpark. So I've seen a lot of answers in the 10 to the negative 6 range. That should be correct. So then let's actually work out the numbers. So I will write this down real quick. I think I'm going to open up a paint window again and try and share it that way, because I don't want to move my whole computer.
I feel like I'm really confused in like the units of this. Like when you were actually like, I don't, in general with the units, I feel like that's what I'm always messing up with. As far as like microcoulombs, and when I'm in coulombs, I don't know what I'm in until I'm like watching another video, and then I'm like, oh, I'm off by 3 decimal points, but I have the right number. It's just wrong decimal points.
Yeah, so That's a
How do
really
you know when you're supposed to be in something wrong? Because I've probably followed your video like 16 times and I keep getting like 0.081 and 0.164. So could that maybe be the right answer, but it should be times 10 to the negative sixth or something?
yeah, either times 10 to the negative sixth, or it could also be times 10 to the negative third, so millicoulombs. With electric calculations and magnetic calculations, because the orders of magnitude are so large compared to what we're used to seeing in physics 1. Because in physics 1, everything we do rounds either 1 or 10. Right? Maybe sometimes you'll have like a gravity calculation with a planet, and then you have to watch your powers of 10. But the next step after you do this kind of like rough approximation, like I did on the whiteboard, is to do the whole problem. But when you do the problem, let's say you get an algebraic expression, like I think I had one like mg tan theta r squared over k one time. Was one that popped up. Well, right here, what I would do is I would keep all the values the same, and I would just automatically pull out the powers of 10. So this is equal to whatever power of 10 is m, whatever power of 10 is g, whatever power of 10 is tan theta, and whatever power of 10 is r squared. And I put that over here. So this is like, powers of 10. And then this is then times the decimal values of these. Powers of 10 over powers of 10 times the decimal values. And that's super duper important for, I'm sure you've realized this, making this mistake, or just having trouble with these problems, maybe not even making a real serious mistake. I'm also going to say that Dr. Cobell isn't perfect, and there can be a coding error in the problem sometimes. So if you get something and you have your work exactly right, and and you've double checked it before you submit it and everything, and you send it to him, he may be able to give you the credit back or explain what's wrong. I know that when I TA'd for this class last summer, that was a common issue because we had just moved everything online. And I don't know how much we have or have not fixed. So feel free to email him.
Gotcha. For this though, like, you gotta, I'm sorry, like I have been on this question so long and I'm just so frustrated by it. How are you getting something to the negative 6? Like, do you mind going back to like having a whiteboard there? Because it's kind of blurry and I'm just lost.
Yeah. Like I said, I'm going to open up a paint window, and I think that might actually be better just because I can write on the screen while I'm talking.
Yeah.
And not hold my whiteboard at a weird angle. And for the future, I'm probably going to have these in my other room where I have a chalkboard so I can stand and talk. But here, let me share my screen, and I will. Okay. So what we've got is G, we've got M, we've got, what is that? Got the charge, Q. No, that's not. Let me look at the problem again. I made a mistake. Yeah. So Q1, Q2, or plus Q2 is equal to, and that's going to be 61 times 10 to the negative 6. And then for T, we've got 154. Oof. And then for R, we've got 0.32, and this is newtons, and this is meters. We want to do everything in kilograms, meters, seconds, newtons. We don't want to use centimeters or microcoulombs or anything like that. Just because when we are working, I think I've mentioned this in a previous help session, but when we're working in physics, generally there's two coordinate systems or two unit systems that we use. One is MKS, meters, kilograms, seconds, and the other one is CGS, or centimeters, grams, seconds. And we do not use CGS at UNCG or in America generally, just out of, I guess, a force of habit. And this is the mass of the green one. I'm going to ignore the mass of the red one. It doesn't really matter for our purposes. And then this one is 9.8. Okay, so we've got that, and I'm going to draw the force diagram again too. mg, I'm going to do the other ones in red because they are the new forces. This is tension, and this is the electric force. I'll do that FC. So FC and FE are pretty interchangeable. One is the Coulomb force, the other one is the electric force. They're the same thing. So if I ever use FE, you know. But so now we're going to get into the meat of the question. Round these, we can write out the equation here, where FE plus mg equals ft, and now we can do our approximations. Let me make that C just because I'm trying to be consistent. That's not right. Okay, there we go. So for FC, we've got KQQ over R squared. And to start, we don't really know the magnitude of Q1 and Q2. We know that they add to this little small number, but we're not really clear on what their actual values are. They could be millions or billions or trillions apart and just have this really small difference. So I don't think that's the case. That wouldn't really make sense with the problem, but we don't know yet. So we're going to leave that right like that. Plus, and then what we're going to do is we're going to start by approximating these. So this rounds to 10. In fact, in 291, 292 with calculus base, we only use G equals 10 because you're not allowed to use a calculator for anything. So you use G equals 10, you use K equals 9, things like that. M is equal to 10, about equal to 10. So what we've got here is 100, or 10 to the 2, as our mg term. All right, I'm going to draw a little line connecting those. Now, over here, we've got Ft. Well, Ft is, it would round, it would be 1.5 times 10 to the 2. And 1.5 is less than 3. So this would be about 10 to the 2. So remember, this is an order of magnitude calculation, so it gives us within one order of magnitude. It doesn't have to be correct exactly. So what we're going to say is then, for best practices, this is also equal to 10 to the 2. Because looking at it over here, I'll write that so you can see it. It's equal to 1.5 times 10 to the 2. And then this is less than 3, so then that's equal to 10 to the 2. And we can come back to this, actually. We can actually work backwards from what we're doing and see what this number is going to be. So this, if we were to leave this as is, this number should be about 0.5. You see that already?
Yes.
Yeah, okay. So because we would have 1 here, 1.5 here, and this is 0.5. So that's already giving us a rough ballpark. But just to make sure that we know how to do, and we're absolutely clear on power of 10 calculations, let's do a quick power of 10 calculation on KQQ. So K is roughly 10 to the 10th, because it's 9 times 10 to the 9th. And somebody correct me if I'm wrong on that. It's been a year since I've done anything with K.
Yeah,
But,
it's 10 to the 9.
So 10 to the 10th, sorry. And then R, we are given as something that rounds to 10 to the negative 1. Okay, now, if we look at this, and let me make sure that that's correct real quick. So R is equal to 0.32 meters. So that's actually either 1, or you could round it down to 10 to the negative 1. That's kind of a borderline case. But if we use 1 or 10 to the negative 1, those are going to give us different bounds that we're looking for. It'll tell us upper or lower bound. So either one is going to be an enlightening thought. So I'm going to say or 10 to the 0. So what we've got here then is 10 to the 10th over 1 times QQ. And then because of this being, this would make this about equal to 0. What that means, because we're doing order of magnitude calculations, is that it is the power of 10 is equal to is less than 10 to the 2. So that's the key distinction. This minus this is 0. So this is equal to roughly 0 compared to these. Does that make sense?
I'm kind of like lost on where we are. Like, is this like the green dot, the green sphere? Like,
Right here? So
like,
this is about 10 to the 2. Mg is about 10 to the 2. Ft rounds to about 10 to the 2. So that means that this has to round to about 0. So when we say about 0 in physics, what we mean is that it is less than 1/10 the other values. So this has to be less than 1/10 the other values for this order of magnitude calculation, which then gives us it's equal to 0. So this needs to be, since this, so 1/10 of 10 squared is 10 to the 1. So it's about equal to 0, which implies that it's about equal to 10 to the 1. And this is the lower estimate because I used the upper estimate for R. So that would give us Q1, Q2 is about equal to 10 to the 9, or 10 to the negative 9, which gives us around an estimate of 10 to the negative 5. And then if I use 10 to the negative 1 down here, I get 10 to the 12 Q1, Q2, because this would be 10 to the negative 2. So 10 to the 12 Q1, Q2 is about equal to 10 to the 1. So we would get Q1, Q2 is 10 to the negative 11th, or 10 to the negative 5th, right around there. So either one we get between 10 to the negative 4.5 and 10 to the negative 5.5. And so both of those calculations tell us that it should be on order of 10 to the 5th for Q1 or Q2. And I know this is sort of long, but it's something that you need to get in the habit of, especially if you've been using a calculator for, I hope that I clarified a little more. I understand that it can be a lot of information to see when you first see it.
what is that 10 to the negative 4, 10 to the negative 5? What is that?
So that's the range of values that our answer should lie inside.
Of what answer? The Q
For
green?
Q. For either one, because they're multiplied right here. Right? And they're going to have close to the same magnitude. If one had a much larger magnitude than the other, we would probably see one of them floating, or something along those lines. But because they have roughly the same mass, and this problem is not a totally, we know it's been written by a human, I'm going to assume that they're close to the same value. So this range is the range of values for the red charge and the green charge.
So this answer of 10 to the negative 4.5, this isn't our exact answer. This is what our answer should be between, correct?
Right. So if I just do everything like you can, let me make sure that I'm not missing anyone here, because I know that I have to admit people. Okay. So okay. Sorry to interrupt. Yeah, so what we're looking for here when we're doing a power of 10 calculation is we're looking for a range of values. And the fact that R, the only reason that we get a range instead of a single number is that R is on the borderline. R is actually almost exactly log 10 of, or like 1/2 as log 10, right? So like it's almost exactly on the borderline. If we have something that's equal to 3-ish, it gives us a borderline value. So 32 was R, or 0.32 meters. So it's about equal to 10 to the negative 1, and it's about equal to 1. So that's kind of a touchy case. Normally, we'll just get 10 to the negative 1. So like, let's say that R was 0.19. We would just get this value. Does that make sense?
I also like keep getting confused because sometimes like numbers, you know, in scientific notation, you keep one number like it's 1.5 times 10 to 2 or something. And then sometimes it's 61 times 10 to the negative 6. So I'm like confused because are we keeping two numbers or are we keeping one number and a decimal?
Okay, good question, really good question. The reason I'm doing this is because I'm using whole units. Okay, so for newtons, I'm doing 1.5 times 10 to the 2 newtons. This one we could do. We noticed for a second though, we didn't use this in the calculation. We didn't use Q1, Q2's power of 10 in the calculation. So it didn't actually affect the calculation. What we were trying to find was another boundary for that. So we're given that their sum is in this range, and then we're given that each of their values is in this range by the calculation we did. That's the only reason I didn't touch this one is because I'm keeping it in units of whole coulombs. If I were to actually do a calculation with it, I would probably make it 6.1 times 10 to the negative 7 coulombs. So you're right. That's a really good question, and it's a pretty astute observation to have. For everything else, I rounded it to basically the closest power of 10 for the actual calculation part. Okay. Now this should, if you are on a test, don't really worry about this. But when you're working on homework problems, especially ones that are giving you trouble, do this a couple times and make sure that you get this same range. This is something that they should teach us in high school, and they definitely don't, is this power of 10 calculation, because every single scientist does order of magnitude calculations, these are called. They're also called Fermi calculations in physics because Fermi used to use them a lot. You ever heard of the Fermi paradox? It's like, why is there no intelligent life? Well, he did that whole thing with just power of 10 calculations. So this power of 10 ranging is super, super, super important to understand and be able to do. So I can look at this problem and do a couple quick mental calculations. That's about 10, that's about 10, it's about 10 to the 2, it's about 10 to the negative 1, and I should get a ballpark already. And this actually, this upper one, or this, I guess this lower one, because it's negative, makes more sense because it's very close to this value. See that?
For my problem, it's a lot different than the examples that I've seen. My balls are attached to each other in a horizontal string.
Okay, and they have the same polarity, so they're pulling apart on the string?
Yes.
So yeah, you're gonna get a similar problem. If you want to email, did you already email me the problem?
No, I can email it to you.
Yeah, if you can email me a screenshot, I will go over that one as soon as I'm finished with this one. This one I'm starting with because this is one that I've heard from like everyone that they're having trouble with it.
Okay, thank you so much.
Yeah, of course. Okay, so let me black this one out, and then we will move on to the actual calculation. So we've got that. Oh no. There we go. So just to do the actual calculation really quickly, and see if we get something that makes sense. We've got F T equals mg, and this time we're not using powers of 10 just because it does not make sense for us to do so. We use that to check whether we're sane and to get a rough intuitive value. And then when we're doing the actual calculation, we can check that against it to make sure it's in the same range, but we don't want to use that as our be all end all. So we've got 154 equals, and that's 9 times 9.8, so that's 76.4. Plus, wait, let me make sure that that's right. So 79.2, I'm sorry. Oh, by the way, this won't be as painful in the future because I am getting a writing pad, so I will be able to write this much quicker and nicer. I realized I needed one because of this. Plus k over r squared 1q2. Okay, and then what we can do here is we can subtract that off and get a value. So we get 154 minus 79.2. So we get 84, 75, 74.8. Equals k over r squared times q1, q2. And then so we get 74.8 times r squared over k. And so that's algebra equal to q1, q2. And I'm sure everyone's gotten to this point. I know that this problem has been a big problem, so I don't want to belittle your intelligence and think that you haven't gotten here. I understand how frustrating this is because I have had to do all these problems like many times over, and this is one of those ones that just a little problem in the code can really screw it up. So now we're going to do exactly what we were talking about before. So Q2 is likely negative. So the magnitude of Q2 is positive. So what we can do is we can replace this with a negative sign. Let me make sure that that's the right polarity. It just says they have opposite polarity. Oh, so the bigger charge is going to be the positive one. That's a key little takeaway. The bigger charge is going to be the positive one because that's how we use larger and smaller. We use larger and smaller to denote more positive or less positive generally. So in this case, we're going to solve for Q green. And to solve for Q green, I'm going to assume that it is the lesser charge, or sorry, solve for Q green. Q green is the lesser charge. So let me do this again. So we've got writing. So Q1, Q2 is equal to 61 times 10 to the negative 6, or 6.1 times 10 to the negative 7. So let's write that. 6.1 times 10 to the negative 7. And then this is, or sorry, 10 to the negative 5. I'm doing that backwards because it's a negative power. That our sanity check works because that puts us in the right ballpark. Times 10 to the negative 5. And then that would be plus Q2. Is equal to Q1. Now, this step has been screwing a lot of people up. It might even screw me up, so let's double check it. We've got 6.1 times 10 to the negative 5th as a given. There's a plus there. And sorry, minus, I just did that. And I'm using magnitudes here. I'm using magnitudes of charge. That's why I have a minus sign here, because this one has to be the larger charge. So this one has to be, this one has to be the negative one. So we can say the magnitude of this one minus the magnitude of this one is the given net charge. So let me actually switch the numbers there since we said that. So see, I made a little trip up and I double checked and we got back to it. And Dr. Covell will tell you this, but the number one mark of a master of something is that they go back and like a PhD or something, is that they go back and check more than everyone else. So they make less mistakes. Like a chess grandmaster just is constantly double checking his choices, for example. So that still gives us this calculation. Because I just flipped the negative sign. So now we've got negative 6.14 times 10 to the 5th plus Q1 is equal to Q2. Because we would get negative Q2 is equal to this minus Q1, and we can flip the signs. So Q2 is equal to negative this plus Q1. So now we can solve by replacing, just like we normally do in the other videos, Q2 with this formula involving Q1. We get Q1 times negative, in this case, 6.14 times 10 to the negative 5. Plus Q1. And does anybody want to work out this quadratic? No? I mean, I can grab a calculator and actually do it, but this is the process. So let me grab my scientific calculator. You all know about Desmos? Okay, so I'm going to share the Desmos screen so that we can all see it, what I'm doing here, and we can double check and make sure that we don't make any mistakes. I don't make any mistakes. That. So what we've got here, and is, why is it doing that? Okay. We've got 74.8 times, and then I'm just going to start replacing values with the proper value, times 0.32 squared divided by And then the value for that is, and make sure that since we're doing the proper values, let's make sure that we're using the exact value of k. 8.987 times 10 to the 9th.
So our formula sheet just has 9 times 10 to the 9th. Do you think that 9 is good to use since that's what our formula sheet uses?
That's fine. Anyways, it was a difference of 0.02. So yeah, you should be fine. So this is this value right here. So let's write that down. We've got, and I'll write that over here, 8.51 times 10 to the negative 10. Okay, equals all that junk. Now, we can actually solve the quadratic. Let me pull this down and I will solve the quadratic. So we've got Q1 squared is equal to, or sorry, minus Q1 times 6.14 times 10 to the negative 5th. And then that's minus 8.51 times 10 to the negative 10. So we've all seen this calculation before, right? Like we've all gotten something close to this point. So now solving for that, we get positive 6.14 times 10 to the negative 5th, because we're just doing the quadratic formula. Negative b, and we're going to start with plus the square root of, and then that's 6.14 times 10 to the negative 5th squared, and then minus 4 times 1 times, and then that's negative 8.1 or 51 times 10 to the negative 10. And then this whole thing divided by, nope. And let's put that all in parentheses so that it'll let me do it right. Yeah, so Desmos is really good because Desmos lets you write it out the way you would like by hand. So I would if you have your home computer and you're doing this, I would check out Desmos, and that's over 2. And so we get a very like sensible figure here for a Q1. It's in that same ballpark. This would be about 10 to the negative 4 in magnitude, because this would round up. So it's very close to that ballpark estimate we were looking at. It's an order of less than an order of magnitude off. So this would be the Q1 value, I'm sorry, this is the Q1 value. And if we go back to our assumptions before, Q1 is going to be the positive charge. And Q1 is going to be probably the, and if I go back to the problem and look at it, why? Q1 is going to be the larger of the two charges, which means it's going to be the positive charge, and it's going to be Q red. And then all we need to do is plug in Q red for the formula to get Q green. So we were given Q1 plus Q2 in microcoulombs. So going back to that. And I will make sure I'm sharing.
Question.
What's up?
Your total charge, it looks, your screen is like really tiny and my eyes are not great, but it looks to be 61. So
Yes.
how do you have 6.14 times 10 to the negative 5 in there? Where'd that come from?
So it's 61 microcoulombs.
Correct. So that's 6.1 times 10 to the negative 5. Where'd the 4 come in?
Let me see. I don't know. I think I just wrote a 4 in. Well,
Okay.
good catch.
I got
I'm-
like basically your answers, but they're slightly off, and I'm wondering if that's why.
Yeah, so yeah, it's because I had a plus sign over here and I'm using the draw pad poorly.
Okay.
So the plus sign and the 1 looks like a 4 to me.
That's fine.
Um,
No worries.
But so I'm not gonna lie, I don't really feel like doing all of that all the way over again, but it should be
That's
like,
fine.
you know,
You're good.
maybe like off in the hundreds place or something.
Yeah.
Okay. So then that means that we still have 6.1 times 10 to the negative 5. And then we can subtract out the value we were given from this most recent calculation. Let me make sure I'm sharing the right screen. Okay, this should be making it much larger. Is that better?
Yeah.
Okay.
Dang. Sorry, I was like, oh my God, where'd the 4 come from? How did we get there? Oh, ooh, I thought I had lost my knowledge.
Yeah,
Okay.
no. I just made a little error because I can't read my own paint drawings.
You're fine. You're fine.
This
Thank
is
you.
why I need that little pen and marker thing.
Is your birthday coming up?
No, but I'm gonna get it
Oh.
anyway. So I get 6.1 times 10 to the negative 5th, and then this is minus our answer.
Quick question.
Yes, sir.
So when we're talking about the power of 10, do we need to like convert from that variable to coulombs, like from UC to C? Like, do we need to worry about that?
So I'm using that's actually what I'm using for all the calculations. I'm just keeping in mind this power of 10. So
Okay.
this is in coulombs, and then our answer, which was in, I think, on order of 10 to the negative 5, if I go back and look at it. So our answer was on order of 10 to the negative 5. It's on the same order of magnitude as our question. And it is also in coulombs, yes. So when you're doing this, he wants 4 decimal places generally. That's what WebAssign automatically goes to, unless you tell it otherwise.
Well, how do we get 10 to the negative 5?
So 61 microcoulombs is 61 times 10 to the negative 6 coulombs,
Okay.
right? And so this is 6.1 times 10. So I just pulled that 10 over and get 6.1 times 10 to the negative 5.
Okay.
And then doing all the rest of the calculations the same way, and double checking and keeping extra careful track of our powers of 10, I got that the other value was on the same order of magnitude, which makes sense. So if Q2 is the negative charge, like we're assuming, and I think the question, if I'm absolutely being honest, I think the question is asking for magnitudes. So yeah, so it's asking for just the magnitude. So for the first one, you should get 7, and for the second one, you should get like 1 something, and those are going to be times 10 to the 5th, and then the units are coulombs. And that's what the numbers that you were given in this problem, and this is Patrick's problem that I got. So Patrick's numbers. If you double check your numbers and just make sure you walk through it this way. The key to the problem that I'm seeing with a lot of people that are doing this is actually happening right here. So this is the problem point. This is the sticking point. I'm saying the magnitude 61 times 10 to the negative 6 is equal to the magnitude Q1 minus the magnitude Q2, which does 2 things. It automatically makes Q2 the negative charge. And it also automatically means that we need to watch our signs. So we're solving for magnitudes. We know that Q2 is the smaller charge. We know Q2 is negative, and we have to watch our signs throughout all this calculation. So down here, for example, this was one that I had to double check. When I solved for Q2, I had to move the negative sign over like that, which meant that I got a positive Q1 minus 6.1 stuff is equal to Q2. So that is dicey. It is something where before I even moved on, I had to double check that a couple times to make sure I was doing it correctly, and I caught a mistake. So those powers of 10 and this sign right here are the points where people are I think getting stuck, and they may not even realize that that's where it's happening. I think Sarah and I went over this like 3 times or something, with this minus sign being an issue.
Absolutely.
Yeah.
Although
So
the good thing is, if you screw it up, there will be a negative under the square root, so it won't work out.
yeah, so that's good. What's a
Nice,
weird
nice.
and interesting fact is that that would mean that you have a magnetic field. So getting a value of I in your electric field calculations is generally talking about rotation, which means you have a magnetic field. And you're not there yet,
That's
and
not
you won't
coming
do that
this
in
class.
211. Sorry, what?
Is that coming in this class?
No,
Oh, good. Woo.
Yeah.
Okay,
you won't ever talk about I.
good. I'll live
Yeah.
my life without it then. That's good enough.
Yeah,
how-
but so
how do
you
we
will
know our
learn about
Q2 is
magnetic
negative?
fields. Sorry, go ahead.
How do we know our Q2 is negative?
So
you say Q1 minus Q2, how will we always know that it's going to be subtraction?
So we know that the net value is greater than 0, right?
Yeah.
And so I'm choosing Q1 and Q2 so that the smaller one is being subtracted, so that
Okay.
I get a positive value.
Okay, that makes sense.
Yeah, so I don't know that we could have chosen Q red and Q green to be either one, and that's why I didn't say red and green, I said 1 and 2. And then now that when we get to the end and we know that Q2 has the smaller charge, then we make sure that it's the negative one.
Okay.
So
Yeah.
at the end, it asks for like magnitude, and can't magnitude like not be negative?
That's correct.
But it says that they have different charges.
That's correct. So the charge magnitude just tells us how far along. So let me clear the screen real quick.
I'm just confused on if both of my answers should be positive or if
They
one
should.
should be negative. Okay.
Yeah, they should both be positive. So when we're talking about magnitude, anything in physics, we're talking about a number line. And magnitude is so like, let's say I'm right here, this is Q1, this is Q2. The magnitude of Q2 is just the absolute value of Q2. And the magnitude of Q1 is the absolute value of Q1. And since these are charged, they're scalars, we don't need to have a vector quantity or anything like that. But if it asks for the magnitude of a vector, we do the same thing, but with the Pythagorean theorem. So we get the square root of a squared plus b squared. And
So
that
when
is
I-
obviously.
So
What?
when I add my magnitudes and it says it equals whatever number, I'm adding the absolute values. Yes.
So yeah, if you get Q1 plus Q2 is equal to this net magnitude of 6.1 times 10 to the negative 5, right?
Mm-hmm.
That is not adding the magnitudes. This is adding the actual charges to get the net magnitude of the system. So this is the net charge magnitude of 1 and 2. So that's this quantity. Or you could even see it like Q1 plus Q2 like this, where those are absolute value signs, right? So that's what this is. Sorry.
So it is assuming that it's adding the absolute values.
It's adding them and then taking the absolute value. I'm sorry, I misspoke or miswrote. So you're doing this to get this number. Okay.
Doing what to get what number?
I'm taking, so I'm taking this absolute value of the whole sum to get this number. Okay. So the whole sum. So this could be positive or negative. This could be positive or negative. Doesn't matter because the absolute value is outside of both of them.
Okay.
Gives me this. Okay, so now what that means is then the reason we got to be careful with the signs, and it might help you if you're having trouble with this, it might help you to always use this absolute value unless you know otherwise. But let's say that we know Q2 is smaller than Q1. So since this is positive and we know they have opposite charge and we know that Q2 is smaller than Q1, we get that Q1 is positive and Q2 is negative. So this would be equivalent to Q1 minus the magnitude of Q2. So there you see the absolute value being pulled off and put on the second quantity once we've sort of deduced that the second quantity is the negative one. So this is, we can do this because we know that they're attracting each other. So they have opposite signs. We know that they sum to this down here by this inequality. And we know that Q1 is bigger than Q2. So I have some big quantity minus something is still positive. So this must be negative. Are we tracking?
Okay.
Okay, does that help?
Kind of.
Okay, so I'm gonna go over it one more quick time and then I will get to the problem that was sent to me. Okay, no, it's fine, it's fine. I actually, this is really good. This is very helpful for everyone, I think. So let's say we
I
have.
guess Q1 is always positive, like that one's positive. And
Yeah,
then
so we haven't said which one is Q1 and which one is Q2. Because they're red and green, right?
Yeah.
So we don't have a 1 and a 2 in our concepts.
My red is positive.
Right. So exactly. So we can choose whichever one we want to be which one later on. Which that sounds a little wishy-washy, but it works out. So we've got this. We're gonna just choose Q1 to be the bigger one because they're opposite. So Q1 or Q2 is less than, and I'm gonna use or here, or Q2 is less than 0 because it has a negative charge. So this is an or, if you're wondering, that's an or. So that means that I'm gonna pick Q1 to be greater than 0, which then implies that Q2 is less than 0 because they have opposite charge. So then we get Q1 is the larger of the two because 6.1 times 10 to the negative 5th is equal to Q1 plus Q2. And this is greater than 0, right? So then our last step is to take this and say, we've got a Q1 and then minus something less than 0 here, plus something less than 0 is equal to something greater than 0. I know inequalities can be kind of hairy to look at and think about, but what you'll find is that the fundamental quantities, like the fundamental qualities of everything to do with physics and math are inequalities. So it doesn't even really matter what the values are, it's inequalities that matters, or ratios. But so this tells us this is greater than 0 because this is greater than 0, which means that Q2 is negative, and which we already worked out, and Q1 is positive because we defined them that way. So we're just choosing, once we get to right here, We're just choosing which one we want to be greater than 0 and which one we want to be less than 0. And it shouldn't matter after that. We know that one has to be greater than 0 and one has to be less than 0 because they're opposite charge. And we know that they sum to a positive. So we choose them so that they satisfy all this, and that gives us this inequality. Gives us Q1, the thing we were using before, minus Q2.
So the positive, like adding the positive and the negative still equals a positive, is what you're saying.
Yeah, so because adding them
Okay.
together is still a net positive charge, then the inequality gives us this.
Okay.
Yeah.
I get
I'm
that.
sorry if I'm trying to think of how like I can improve my wording on this. I know that it's a little it can be a little dense when you have a bunch of inequalities, but these are the mathematical backing for what's happening that lets us reason. So it's this and this, these two right here, and those two combined allow us to reason out that we can pick one bigger than 0 and one less than 0, such that we get a positive number. So those lead to this one right here, which takes us back to our original premise. So follow the arrows, these two, and then the brown arrow to this one. I will. Does that help?
Yes, I'm good. Thank you.
Yeah. Okay. Cool. I know that, like I said, I know that I can be a little wordy, but I think it's the more fundamental of the concepts is the inequality there. So okay, I've got another question that I'm going to go over here. That was one that here's one that I think I just got. Okay, so this one, I might even make a video on this one because I actually really like this problem. So we've got two charged green spheres on a frictionless horizontal, or two charged spheres on a frictionless horizontal surface are attached to opposite ends of a string and are in static equilibrium. The 34 kilogram red sphere has more charge than the 12 kilogram green sphere. Okay, so we've already got the same inequality. Already, we're running into the same exact inequality. We've got Q1 plus Q2 is equal to something. If I pull that up, 964 microcoulombs, so 9.64 times 10 to the negative 4. Okay, and we know here that one of these is less than 0, so Q1 or Q2 is less than 0. So we can then say that the positive charge, because this is greater than 0, the positive charge has to be with the one which is greater than 0, and the negative has to be the one which is less than 0 in magnitude. So we get here that Q1 plus Q2 is greater than 0. And let's choose Q2 to be less than 0. This implies that Q1 is greater than 0. And this reduces this to Q1 minus the magnitude of Q2, just because of the way we chose those numbers, is equal to 9.64. Oh, that's such a bad 6. Oh, whatever. Times 10 to the negative 4. Okay. Now we've got the sticking point, the thing that everyone's been missing, the thing that I had trouble with. We've got that. We've got that out of the way. We've got it worked out. Later on, we'll know which one's positive or negative by the wording of the question. like which color is positive or negative by the wording of the question. But this is our fundamental inequality to start this. So
Excuse me.
go ahead.
I'm sorry if you've mentioned this before, but wouldn't it be 10 to the negative 6 because we're converting it to coulombs, or do you want to keep it in microcoulombs?
So it's 964 microcoulombs. So
Yes.
that's 964 times 10 to the negative 6.
And then just move the decimal. Okay.
And I did that, so I get 9.64. So I get that.
But what would it matter if you just left it as 964 to negative 6?
It wouldn't necessarily matter as long as I'm really careful. But now we know we have something about equal to 10. So this is about actually, altogether, this is about equal to 1 millicoulomb, right?
Yes.
And this makes it abundantly obvious that it's about equal to 1 millicoulomb.
Yeah.
So we can double check our answers if we have to do a power of 10 calculation because we miss it the first attempt. We can double check our answers by using a millicoulomb.
Okay, thank you.
Yeah. And then also, we just, in scientific notation, we want to have leading place be right before the decimal, just as a matter of tradition. It doesn't actually affect the answer at all.
Okay. I was having problems with it, and then I sent my calculations to Dr. Covell, and he said I just need to replace the 964 with 10 to the negative 6. But when I tried solving that mathematically, it didn't work out. It gave me non-real numbers.
Okay, so if you're getting like imaginary numbers,
yeah,
it's probably something to do with this inequality more than it is with these numbers.
Okay.
And he's not going to see that right away, nor would I. I mean, that's like you have to solve the whole problem, and a lot of times we're grading or working on other problems.
Yeah.
Because we're both active researchers, so the only time we get to do research is when we're doing TAing and teaching in the summer. But
makes sense why he's not having lectures.
yeah, he's not having lectures.
No, there's no lectures at all. None.
No, we just teach ourselves.
Okay,
You're it for us.
if that's the case, I can probably start offering this every day. I'll just have to ask him.
Well, if you did that, you would be the
Yes,
you'd be the
please.
Yeah,
greatest.
you would be the professor though. That doesn't feel like fair
It's
to you.
not fair. Like you should. At least you should.
That's
be
not your job. That's
Well,
his
here's a
job.
fun fact
Dr.
at
Caldwell
UNC
should
You guys are
be
missing the
that.
point. You're missing the point. I fucking love physics.
Wow.
Yeah. I
Yeah,
think he likes to do it, so why not?
yeah. Like I mean,
Oh.
I am already a TA for the calculus classes and the modern physics class and stuff. And I like to keep my chops up on this stuff because we don't ever really even use algebra like this. We work more with just like the scalar quantities and stuff. And I like these problems, so I don't see why I wouldn't do it. Plus, it looks really good on my resume. I could get like, letters from you guys when I apply to grad school in the fall saying that I basically taught the whole class.
Oh, deal.
Bro, God,
At
bro.
UNC, like every single math class is taught by TAs.
Yeah. So I'm a math major actually. And yeah, basically your entire grad school is just teaching like algebra. But
That's why I take them elsewhere during the summer.
yeah. I mean, so the problem is that the algebra classes we teach and the pre-calculus classes we teach, I know this is a total tangent, but the algebra and pre-calculus classes that we have to teach are technically stuff that people were supposed to learn in high school, but high school teaching is even worse. So like, for example, I failed all of my high school math classes, every single one, to a class. And then when I actually had to use math, I taught myself the math eventually. And it just because it was just stuff like, trig identities and like basic algebra stuff, like these inequalities and stuff. But because I ended up having to use it and like learning it that way, it stuck. And they don't teach that way in high school. And in fact, most teachers who teach calculus or physics in high school don't actually know calculus or physics. They're teaching off of an AP curriculum, and they're not required to know the material. So there's there have been surveys that have been done where they've had teachers take the final exams for their class in math and physics, and they fail in high school classes. So what that means is that when you get to college, you have these people who are ready to move on and these other people who aren't. And the people who aren't ready to move on yet sort of just get handed to the grad students who aren't ready to teach yet either. So you have the blind leading the blind for the lower level classes, which just screws everyone. And then for the upper level classes, you have like the best professors who are mostly researchers teaching the people who are well above everyone else. So you get worse stratification. And our physics department is trying to fix that. That's part of the move to WebAssign and everything, but it's still, don't share this with them if you ever talk to them, but it still leaves a lot on me because I like to go in and make sure everyone's getting everything. Or else what's the point? You're paying for the class.
We appreciate you.
Of course. So now we've got our inequality. I'll step back and we can work on this problem some. It actually ends up, I think this was sent to me by Ms. Gazal. Is that how you say it?
Yes, that's me.
Okay, yeah. So it actually ends up solving the same as the last problem, but we'll work through it a few steps just to make sure that we've got it.
Yes, please.
Uh-huh. And so let me erase this. And I'm going to leave our inequality there. And I'm going to write all of our knowns up here. So you'll usually see me do this on the Blackboard problems too. I'll write all of the unknown quantities up in all the knowns and unknowns up in the right hand. I find for me personally that just doing that is enough to help me work out what I'm looking for and how I got to go about looking for it, because I start to see everything I have and then what I don't have. And only then do those equations on the equation sheet actually make sense. So we've got that they have no friction, which is really super helpful and nice. We don't need the masses necessarily then. Total charge. Tension is 3422.5 newtons, and they are 7.78 meters apart. 3.425 times 10 to the 3 newtons, and then R is equal to 0.78 meters. So I'm going to just use 0.78 so I don't have to use a 10 to the negative 1. Now, so the really fun, nice thing about this problem is that, you know, if I draw the diagram here, there's the center of our spheres, here's the ball, the rope attaching them. There's no friction. We don't need to account for the normal force or anything. In fact, it doesn't really matter at all what their masses are, because we have this tension and there's only one force that we're concerned with, which is the lateral force from the charge, right? So that doesn't mean it's trivial seeing that. That doesn't mean it should be immediately obvious, but we're unconcerned with anything but these. And because of the way tension works, we only need to work out the tension on one side and treat this as like an origin. So we get the whole thing, right? So if we just treat one point as fixed, it's like a lever or like a physics 1 tension problem. We can treat either side as fixed and solve for the other side. So let's solve for this one. We've got, if we do a free body diagram down here, we've got Ft. And then the only other force that we are concerned with is literally Fc. Here, right. F, and we're given Ft. So we can set an inequality here, or set an equality, I guess, 3.4225. Oh, if you're wondering why I use the term inequality for these things that look like a regular equality, it's because any absolute value is an inequality. We don't know the actual magnitude of an absolute value, so it's an inequality. We know that it's greater than this and less than this are both solutions to it. So we've got this times 10 to the 3 is equal to k q1 q2 over r squared. And this is really nice because we can solve this sort of the same way as last time, where we get, if we move this down, let's say we're solving for Q1, we get Q1, which is the positive charge, I'll put that up here, is equal to 9.61 times 10 to the negative 4th plus Q2, negative. Like the only unused index spot on a number is this one, because even this means something in algebra. So we've got all this, and then we get to replacing this with the form we just got for Q1. So we get 3 point, let me change the color here. 3.4225 times 10 to the 3 times r squared over k is equal to 9.61. That's a 6, right? Yes, that's 6. 9.61 times 10 to the negative 4. Oh, come on. Hold on. Started writing like 3 inches above where I was writing. Times 10 to the negative 4 plus Q2, and then that's times Q2. And remember that this is the magnitude of Q2 that we're using. We're using the magnitude of Q2. So the actual value, because we chose Q2 to be negative, is going to be a negative value. But we're only looking for the magnitude, so it doesn't matter. So let me clear up a little space, and then we will proceed to complete the problem. Here we go. Now let me leave that.
So right now we're basically solving for Q2, basically.
That's correct, yeah. So we solve for Q2, and then because we have the sum of Q1 and Q2, we're given Q1. And so then we get, just making sure we write this out properly. Oh no, I covered up our, what is it, 0.73, 0.72?
R is 0.78.
0.78, ooh, that would have been bad.
Okay.
No, it's fine. So then we get, and we can go back to the Desmos calculator and do this again, 3.4. Let me actually do that. So I'll go to the Desmos calculator, I'll share that screen. Okay. Desmos, and I will open my Paint. So yeah, it only lets me share one like window at a time. So I'm sorry if this is really small or the right side is really small or anything. Times 10 to the negative 3 times, and then we're going to do r squared over k, 0.78 squared. No, not to the 20. Goodness. And then that's over, divided by 9 times 10 to the 9th. So now we've got our, making sure I do that right. Yeah, so now we've got our value for the quadratic. So let me write that down and real quick, and then we'll do the second calculation. So we've got 2.31361 10 to the negative 13th. Be a negative. And that's going to be our C value for the, the quadratic formula, b squared minus 4ac, that's our C for that. So then we've got let's do Q2 squared plus 9.61 times 10 to the negative 4th Q2 minus 2.31361 times 10 to the negative 13th equal to 0. Solved for our quadratic formula. And now let me plug all that in, see what we can get. Oh, cool, I can leave that up. All right, so we get negative 9.61 times 10 to the negative 4th. So that's negative b. I'm going to put this in a double parenthesis. Plus square root of, and then we're going to get 9.61 times 10 to the negative 4th. Minus 4 times this quantity. So I'll just copy paste that. Oh, okay. Well, it won't let me paste it, so gotta type it. 2.31361 times 10 to the negative 13. And then make sure that I have everything in the proper parentheses. And then that's going to be over 2. And then this is in coulombs still, because we solved for it in coulombs. So Q2 is going to be 0.015 or so, 0.01502 coulombs, which is in millicoulombs, right? So it's going to be 0.015 coulombs is going to be 15 millicoulombs. So that's a pretty hefty, that is a pretty, oh, nope, small mistake that could have crushed everything. There's a square there. So I'm glad we caught that. So that's b squared minus 4ac. Let's try the negative sign. Squared minus 4ac. So I'm getting a negative value. I don't know, I'm not positive from what I've written down so far that I've made a severe error in the signs on the 9.61. So again, I'm going to take this back to our inequality and double check. So we can actually just do this as in terms of Q1 instead, so that we're working with a positive quantity and it might be better.
For the value, like when I calculated it, for Q red, I got 9.61 times 10 to the negative 4 coulombs.
Yeah, so that's actually essentially exactly what we just got. Like,
yeah, exactly.
So
But that was incorrect. So
okay, so if I look back at the problem, and I make this bigger, 9.61. So you have 9.618 times 10 to the negative 4. And if we look at it, so that's actually going to be the smaller of the two charges, I think.
oh, so is it correct? I just switched places.
Yeah, I think so, because we set Q2 to be the, oh, see, I made a mistake on this one. I made a mistake.
Is it the same mistake I made? Because we got the same answer.
Well, so I treated them as opposite polarities.
Oh,
Mhm.
I see.
So let me
We
share
just
my
added
screen.
them.
We would solve it the same way, but we would make the sign on Q2 negative. You're probably right. You're probably gonna get the same answer, but with like flipped values. So the larger charge is going to be the other number. But let me double check that with a negative sign and see if we can fix the issue here. So make that negative. And then because of Desmos, I can just go back in and fix it.
I'm sorry, quick question.
Yes, sir.
So when we have, could you like show how to convert from millicoulombs to coulombs? Because it's like every time I get confused on like how we're gonna convert from -6 and from 10 to the -6 to whatever we need.
So coulombs is if you're doing it on Desmos on like a web calculator, millicoulombs is 10 to the -3rd, microcoulombs is 10 to the -6, and then you just make sure that you keep that with the number whenever you're doing the calculation. What I had for a really long time as my background on my phone, just so I could memorize it, was like the powers of 10 names. And so if you can find a way to make powers of 10 make more sense, I feel like that is not even going to be an issue for you. I know that they're tricky to start off because they are, I guess, powers of 10 are a mess. I know there's a lot of them, but you're really only, for this class, you're really only working in, you're going to have mega, maybe, rarely. You're going to have kilo. You're going to have milli, centi, and micro and nano a lot for the coulombs. So nano sounds like 9. So it's 10 to the -9. Micro is 10 to the -6 because it's not nano. That's just how I remember it. Milli is like a millipede because millipedes have 1,000 legs or 1,000 feet. That's what the Latin people named them, or the Romans, I guess. And so when we're converting for coulombs, we just want to make sure that we take, like, let's say we have 968 microcoulombs. So that's 968 times 10 to the -6. So those two numbers are together, right?
Yeah.
And then if I want to make that just a 9.68, I take that 100 and move it over, and I get 9.68 times 10 to the -4.
And that, so, but how do we know what coulombs is, like the original form of coulombs? How do we know?
So coulombs is 10 to the 0. It's a 1. It's value
Okay.
times 1. The coulomb is actually defined, if you want to think about where it came from for a second, the coulomb was defined by Auguste Coulomb taking 2 balls of metal and just rubbing them with cat fur for like days and days and days and days and days and days until they were attracted to each other. There's 2 kinds of charge. There's cat fur charge and amber charge. That became positive and negative later. But so a coulomb is a really huge amount of charge. I think I talked about this last time too. Like a coulomb is like, if you were to get shocked, if you had a coulomb of electricity pass through your body in like a second, it would be way more than enough to kill you. So the unit of current is actually coulombs per second. And you're going to see very small amounts of current when you start working with current for the same reason. So when we're doing these problems and we're seeing these balls that are in kilograms and they have tension pulling on them and stuff like that, what we're looking at is probably microcoulombs. So we're getting 10 to the -6 coulombs. So that's 968 times 10 to the -6, just straight up coulombs right there.
Okay.
Yeah.
But the final answer, we usually put capital C, which is coulombs. So I was just wondering, like, how do we go from what we got in the answer to our final answer, which is in coulombs?
So the final answer, if you have anything in terms of charge, so like if you're able to get an answer in millicoulombs or microcoulombs or something, you already have it in terms of coulombs. You just got to move the power of 10. If it's a question about how you type it in the answer, I usually do times 10 to the whatever coulombs. Sometimes it doesn't like that. And then that's a problem for Dr. Covell, and not me, because I can't, for this class at least, I'm unable to go in and edit the code and fix stuff. So just convert it by typing 10 to the negative whatever for the units on the actual WebAssign answer.
Okay, so we don't have to convert?
No, you don't need to convert as long as it's in just straight up coulombs. If you have something in millicoulombs, then subtract a power of 3 from the 10.
Okay.
Yeah,
Thank you.
of course. So, Ghazal, I'm sorry I made a mistake. I'm gonna actually write up a video of that one later that you can go back over, so I don't have to resolve it and use the Paint app, because the Paint app is a pain in the butt.
Well, thank you so much. And yes, I would love a video if you get the chance.
Of course. And then I'm gonna also post a video probably going over some of the conceptual questions people have been having. There was one, let me double check and make sure that I have the right person, or the right question. So I have one from you about the lab as well. I have one from
the lab. There's still a few in the lab that, like, I don't know, I just didn't understand. And then when I would ask my teacher, he would explain it, but I still wouldn't get like what he's saying.
Okay, so the one of the big crappy things about the lab is that I cannot see the lab. So I'm glad you sent me a screenshot of what's happening, but I am absolutely.
I can send you all of it, sir. No problem.
So let me share my screen, and I can just talk about this for a minute. I don't know, with the labs actually solving it, it's going to be a little more difficult than just sort of like talking it out. But so here's the diagram you sent me.
Yes.
Okay, so can you voice your question better so that I can talk about it?
Yeah, so the question was basically asking to solve for the magnitude of the value, and I think I figured it out. Okay, so and it was asking for the x and y components. The y component is 0. And then for the magnitude, I was wondering if we would use the formula V equals the electric field times the distance. So if they've already given us V, which is 2.86, we would just need to solve for E, because we know the distance is 250 centimeters.
Okay.
Right?
Yeah, that's correct. So potential, it says equipotential, right? I'm gonna draw something on a whiteboard real quick and then show you guys. But when we draw the equipotentials, equipotentials sort of act like integer markers on the derivative of this thing, or vice versa. So what that means is that, like, these lines are the slope of the potential.
Okay.
So these arrows tell us that the potential line, the next potential line is in this direction. The next potential line is in this direction, right? So you've got your marker there on an equipotential line. And, the y value is 0. The x value is going to be the distance from, I don't know if it's asking about the distance from the positive or the negative.
They're both the same because they give us directions, but them 250 centimeters apart.
Okay, so if they're 250 centimeters apart, you can pick the origin where you're at. You can pick the origin from the positive or the origin from the negative. Any one of them is going to give you what, 125. But so working out the actual potential here, you want to figure out KQ over R for the negative charge, and KQ over R for the positive charge, and add them. Does that
Oh, I see. Okay, yeah, that makes sense.
Yeah, so because they're linear and the charges are likely each charge is of 1, you're going to get like 2 kQr.
Okay.
Yeah, that seems correct to me from the top of my head.
Okay, I'll try it again.
Yeah, and then the only other option that you might get is that okay, so let's talk about these field lines for a second. So these field lines, these are the actual like fundamental thing that is electricity. We normally think of electricity and magnetism as being like, circuit through a wire, or like current through a wire or something. But to an electrical engineer, to a physicist, to a mathematician, to anybody who works with electricity, the fundamental thing is actually these arrows themselves. They're like markers of the vector field. So what these arrows mark is the electric field, and the electric field is force per charge as a function of location. So it would be like F over Q of XY. Yeah, so potential is F over Q times D, you're right, but it's also the potential energy per charge.
Which is why we'd have to solve each one individually and then add them.
Right, so we solve for the potential energy per charge from this one, and the potential energy per charge from this one, and we should get something. So it's better to think of potential energy as potential energy per charge than it is field times distance, because the field is a vector quantity, and so you have to have directionality.
Yes.
But the potential energy and the potential are scalars that just tell us some number for location, not a number with a direction.
Okay. And then for the charge, they didn't give us any values for the charge. So how would we find that?
So for the charge, if you're not given a value for something, assume it's 1.
Okay.
So just like if you get a calculation that's pretty difficult, or like you're doing, comparison calculations where you have to find the ratio of one thing to another, you would just assume that it's 1, then work backwards.
Okay, that makes more sense.
Yeah, so you can see my screen where I'm talking about the field, right?
Yes.
Okay, so the reason that it's better to choose potential and potential energy in most cases is that to calculate the change in the potential energy as a function of the field, you have to do what's called a line integral, which is a like calculus 4 or like vector calculus concept, where I have to say, okay, so along this path, here's how much I gain, right? And it's not always as simple as a plus or minus. It's not always what we call a conservative field. But if we can take potential energy, we can get the field from that much easier, or potential, we can get the field from that. So I'm going to post a little infographic later on that talks about the relationship between the field, potential energy. It's some stuff you've probably already seen in like the web textbook or something, but I think that for problems like this, you want to solve for the scalars first, because scalars are simple.
Okay, that sounds great. Thank you.
Yeah, of course.
Hey Ghazal, what did you get for the X component, and how did you get the X component?
The X component of,
sorry, go ahead. You go ahead.
sorry, go ahead.
No, I said you can go ahead and explain it to me.
Okay, so the X component of, are you talking about the force or the field?
Electric force.
Okay, so the X component of the force is actually going to be the net force in this case. And the reason is that for this diagram we're looking at right here, it's along what we would call the x-axis, right? So since it's along the x-axis, if we were to draw a little force diagram, there would be nothing pulling it up or down. It's sort of just like going straight along the axis. if we were to try and find the y component, it would be 0, and the x component is going to be the net force in this case.
Which you said was 125?
So the distance is 125 centimeters, right? So it's 1.25.
No, it's altogether from the positive to the negative charge, it's 500 centimeters. And then from the positive charge to the center and the negative charge to the sensor, it's 250 centimeters.
Oh, so each one of these is 250.
Yes.
Okay, so you get 2.5 as R, right? So let's just use meters for R. We're gonna get 2.5 here and 2.5 here. And so KQ, the field in this case, is gonna be KQ over R squared. And then over here, it's gonna be KQ over R squared negative.
Yes.
And because of the fact that they're vectors, it's just gonna be added. So the force from this one is gonna be added to the force from this one in the same direction. So it's going to be almost like you have 2 of this one. This one's pulling on it, this one's pushing on it.
That's how you said to solve for the magnitude.
That's correct.
And so the magnitude would be equal to the value of the x component.
Right. In this case, because the y direction is essentially 0, you're at 0.1 degrees off of the median line here.
Yes.
You just solve for it that way. Yeah.
So your x will be KQR squared minus KQR squared?
So it would be KQ over R squared for this side, and then negative K over negative Q R squared on this side. So
Wouldn't that give you 0 eventually? Or
no, so this one, the Q is positive, right?
yeah.
And this one, the Q is negative. And so then the reason we're adding that negative sign is the direction as well. So this one is from the negative direction and this one is from the positive direction. So what we get is a positive in the positive direction and a negative times the negative direction. So we get a positive and a positive, or
Okay.
a positive and a negative times a negative.
Okay.
Does that make sense?
Yes, sir.
So you can think of this one as like something reaching out and pushing on it. And then this one over here is a tension force almost. And if you think about those together, they have to add. They can't, this one can't subtract because tension can't pull. Right?
Yeah. Yeah, that all makes sense now that you explained it. Thank you.
Yeah. The arrows are what's going to give you that intuition over time. So you're going to look at the arrows and say, okay, things flow into the negative and out of the positive. And so if anything has a net negative, it's going to be tugging, and anything has a net positive, it's going to be pushing. And so you can get that intuition, oh, I need to add these because the negative is on the opposite side of the positive. Oh, I need to subtract these because they're on the same side, right? So like, let's say that, I don't know if I can do it, but let's say I have a charge out here. Like, do you see my mouse?
Mm-hmm.
So if I have a charge out here, then the negative and the positive are sort of on the same quote unquote side of my charge, right? So I'm going to be pulled by or pushed by whichever one is closest. And if I have a charge on this side of the positive, right, then the positive, the distance to the positive is much, 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 much smaller than the distance to the negative. So I'm only going to really feel the positive. Does that make sense?
Yeah, that makes sense.
Yeah, but if I'm in the middle here, I need to think, okay, so this one's pushing me and this one's pulling me. Over here, this one's pushing me and this one's pulling me. These lines flow the same way.
So
There were a few other questions on the lab that I didn't get. There was only like 2 left, but I can email you those 2 if you would like.
Yeah, sure. So I know that we've been on here for, what is it now, roughly?
Oh yeah, I didn't mean to do. That's why I meant you should leave if you're probably hungry or tired.
It's okay. Yeah, once I started making dumb mistakes on here, I realized I was tired. But let me stop screen sharing here for a second. And let me check my email. I know that there's probably at least one other person who I said to email me a problem. Or if you're still on here and I haven't answered an emailed problem, let me know.
yeah, I had emailed you about the lab as well, but I have to pull it up again.
Okay,
Which part of the lab? Maybe we're stuck on the same one.
Let me see.
okay, so I think I see, it's the, what, between the charges, like what shape do they take and stuff like that?
Yeah.
Okay, so,
Yeah. That.
okay. So you got how much work would be done if a positive test charge with Q equals +1 nanocoulomb moved from the first equipotential line to the second. So we've got, I can't see I don't think I can see the picture that goes with this question, but when we look at equipotential lines, what we're looking at is that that is the potential energy per charge at that distance, right? So I'll share my screen so you can see. I will do a little paint thing again, and then after this, I'm gonna definitely get off. Is that okay?
Yeah, of course.
Okay. So share, right? Move it over. Let us clear all this off.
Question, will you like post this recording?
I don't even know if I've been recording it.
I think
You're not recording. Actually,
Okay.
you are recording.
The dots up there, you're doing it, I think.
Okay, then yeah, if it's recording, then I will absolutely share it later.
Okay, because I don't have the lab in front of me, but I know I'm gonna need this.
Yeah, I can definitely do that for sure. So yeah, let's look at, let's say I have I'm gonna call red positive. Let me have a red positive charge here. This is my red positive charge. And I'm gonna have some equipotential lines just around this charge. I don't know if your diagram had more than one charge, but it ends up being the same either way. So here's my potential lines. And these are each essentially, as long as the scale is given, these should each be one joule per coulomb. Okay? And it might give you a different scale. Like it might say that these potential lines is like a millijoule per coulomb or something like that. But the potential lines generally, not always, but generally represent an integer value of X per coulomb, or, so joules per coulomb in this case. So if I have a nanocoulomb, so 1 nanocoulomb times, and then let's say I have, this is 1 joule per coulomb from this first to second one. Let's think, this is pushing, right? This is moving outward. So I'm going to lose 1 potential energy here. So it's going to be 1 nanocoulomb times -1 joule per coulomb. So I get -1 nanojoule in this case. Now, the only problem that I think you could be having when I go back and look at your question, because I can't see like I said, I can't see the lab itself, but I can kind of get an idea of what you're doing. So let's say I have a blue charge over here that's negative. That's going to be a negative charge. It shouldn't actually affect this. So these have the same lines. It may seem strange, but that's because, oh, hold on, no, they don't. If they have the same charge, they would have these same lines like this. But if they have different charges, then their lines also add. So you get these nice, neat little potential lines, right? So here's my blue, here's my red. And what I get here is that I get potential steps from A to B, right? So if I'm moving, the force is pushing me along this direction the whole time. And then the force would be pushing me along this way out here and this way out here. So I can actually kind of like draw these like this. And so an interesting fact about electromagnetics is that the potential lines and the potential that are always exactly at right angles to the field lines. So if I can draw the way that the force or the field is moving, I can just draw a bunch of lines at exactly right angles to those, like that. Right there is a right angle. That right there is a right angle. This is a right angle here. And these are always right angles along this line. So as long as every angle is a right angle, then it actually does in fact represent the potential lines. So in this case, it's actually the same. So let's say I step from this line to this line, and I have 1 nanocoulomb, and this is a potential difference of -1 joule per coulomb, because I'm moving towards the negative. Hold on. So if that's the case, I'm going to get 1 nanocoulomb times -1 joule per coulomb, and I'm going to get -1 nanojoule. Right? So work is done if I move this way, because I'm essentially my particle is losing energy, and work is not done. Work is done by the particle if I move this way, and work is done on the particle if I move this way. So if we look at the wording of the question, how much work would be done? Oh, that's so vague. But how much work would be done if a positive test charge moved from the first equipotential line to the second? So let's say that it's work done on the particle. So that means that that's going this direction. So there is there's going to be 1 nanojoule of work done. And try not concerning yourself with this sign to start. And if you miss it, how many times do you get? You know?
6.
Okay, so don't concern yourself with the sign to start. Just work out the magnitude of the change in energy, right? Be absolutely certain, if you can, of this change in energy right here. Oh, oops, I just wrote right over that. Be absolutely certain of how much change in energy you get from moving one to the next, right? And then you should have 2 options. One is a positive and one's a negative. Because he so vaguely worded that lab, I would assume that it's going to be positive, though it might just be the negative. But the number
It should be about like how much space that we had originally measured from the, like right above it is a paragraph, and we had to subtract the 2 values. So you're saying one of those values is what you're circling?
Okay, yeah, so in this case, the potential difference, I see what you say now, yeah. Potential difference between 2 of the equipotential lines, you got it right, is 4.5 volts. So that's, again, volts are joules per coulomb. So that times 10 to the -9 should be the work done. So just try making sure that you have the right number of zeros and then flipping the sign. To me, it looks like you have 1, 2, 3, 4, 5, 6 zeros. So you did a microcoulomb charge calculation.
Oh, so I just did probably the wrong calculation.
Yeah. Yeah, and I don't like how vague his wording is. How much work would be done?
Mm-hmm.
Is the work done on the particle, or is the work, is the particle moving? So is the work done by the particle?
Yeah, like which, yeah.
Yeah.
Well, thank you for all of your help.
Of course.
Yes, thank you so much.
Yeah. Like I said, I will post a video of the tension problem later with the 2 balls on the same sloping or the same unsloped surface. And I will let you know when I post it with a Canvas announcement. And I can plan on doing this again tomorrow morning if everyone wants. I can start doing it pretty much every day at 11.
Yes.
That would be great.
Okay, cool. Yeah. Email me if you have any pressing issues, but since we're doing it every day, I can start working on people's homework problems on here or like lab problems on here every day. So I'll see y'all tomorrow.
All right, thank you. Have a good day.
You too. Bye-bye.
Thank you.
Mm-hmm.